A beam of light consisting of two wavelengths 650 nanometer and 520 nanometer is used to illuminate the slit of a Young's double slit experiment. Then the order of the bright fringe of the longer wavelength that coincides with the bright fringe of shorter wavelength at the least distance from the central maxima is. See the location, if you see the fringe width beta is lambda d by d. Fringe width beta is lambda d by d. So more the wavelength, more is the width of the fringe. So if the fringe width is bigger, okay, suppose you get a third bright fringe in the location x with the smaller wavelength lambda dash, you are going to get more fringes. You are going to get more fringes. Correct? If this is a third one, if you look at this with the smaller fringe, this happens to be, I think, the sixth one. Correct? In the same location. From the central maxima, at a least distance from central maxima, the order of the fringes for two different wavelengths, at least differs by order 1 at least. So if this is a nth order, at least it must differ by n plus 1th order. Lesser the wavelength, lesser the fringe width, but more number of fringes are formed. So that more number should be at least more by 1, if not more than 1. So for a least distance from central maxima at a position x, for the second wavelength lambda 2 d by d, the order of the fringe must be at least n plus 1. Then for a larger wavelength, the order of the fringe obtained there is n. So that is n lambda 1 d by d. So d by d cancels off. Now n lambda 1 should be equal to n plus 1 lambda 2. So now the wavelengths are given. The larger wavelength should have the smaller order in that location. So it is 650 nanometer is equal to n plus 1 520 nanometer. Nanometer cancels. This is 13 4za or 134za. This is 5za. So n plus 1 by n is 5 by 4, implies the order of the fringe due to the larger wavelength is 4. Hence option D is the right answer.